All right, let's jump right in. We're going to look at two totally different ways to solve problems in computer science. You've got the greedy approach, the one that goes for the quick win, versus the divide and conquer strategy, which plays the long game. So just think about it for a sec. If you're faced with something huge and complicated, what's your gut reaction? Do you make the best choice you can see right now and just hope it all works out? Or do you step back, break the whole thing down into tiny, manageable pieces, and solve it that way? Now, before we go any further, we gotta be clear on what an algorithm actually is. It's not some kind of magic. Really, it's just a recipe, a super precise, step-by-step set of instructions that a computer can follow to get from point A, the problem, to point B, the solution. To make this a little more fun, let's think of these algorithms as having personalities. In one corner, you've got the impulsive sprinter, all about speed, making a decision, and moving on. And in the other corner, you have the strategic planner, the one who's patient, sees the whole board, and thinks a dozen moves ahead. First up, let's meet our sprinter. The greedy approach is all about one thing, making a choice that looks best right here, right now. The key phrase here is locally optimal. A greedy algorithm isn't worried about the big picture. At every single crossroads, it asks itself one simple question. What is the absolute best move I can make right this second? And then it does it. No hesitation. A classic example is making change. Let's say you need to make 36 cents. The greedy way is to just grab the biggest coin you can without going over. So boom, a 20-cent piece. Now you have 16 cents left. What's the biggest coin? A 10. Now you've got 6 cents left. You see where this is going, right? Grab the 5 and then the 1. It's simple, it's lightning fast, and in this case, it actually works perfectly. And this really gets to the core of the greedy mindset. It's all about commitment. Once a greedy algorithm makes a choice, that's it. It's written in stone. It never looks back, never second guesses itself. It just deals with the consequences and moves on to the next immediate win. But, and this is a big but, here's the trap. This picture shows it perfectly. By always taking the steepest path uphill, the best local choice, our greedy climber can end up on top of the smaller peak, M. It feels like a win, but it completely missed the actual highest point, the global maximum, M, which was just over on another path. That's the risk of being short-sighted. Okay, time to switch gears and meet our strategic planner. This approach couldn't be more different. It looks at a big problem and says, nope, not going to tackle that head-on. The whole philosophy here is that if a problem is too big and intimidating, just chop it up. Keep chopping it into smaller, identical pieces until the pieces are so tiny that solving them is a total no-brainer. That process of a function calling itself over and over on smaller bits is called recursion, and it's the engine that makes divide and conquer run. And it pretty much always follows this same three-step dance. First, you divide the problem. Second, you conquer the tiny, simple subproblems. And third, you combine those little answers back together, piece by piece, until you've built the solution to the original big puzzle. Merge sort is the absolute perfect poster child for this. You want to sort a long jumbled list of numbers? You just split it in half, and split those halves in half. You keep going until you've got a bunch of lists with just one number in them, which are, already sorted. Then you just start merging them back together in the right order. It's elegant. And this strategy is just incredibly powerful. It makes some ridiculously complex problems manageable. Better yet, because you've created all these independent little subproblems, you can throw them at different computer cores or even different machines to solve all at once. That's called parallelism, and it's why this approach is so perfect for modern computers. Okay, so we've met our contenders, we know their styles. Now let's throw them in the ring with a real-world problem and see how they do. So here's the challenge. Imagine you're in charge of building a road network to connect a bunch of different cities. Your budget is tight. You have to make sure every single city is connected to the network, but you have to do it using the absolute minimum total length of road. In computer science, we call this finding the minimum spanning tree. And here's where it gets really interesting. A little plot twist for you. The two most famous ways to solve this problem, algorithms called prims and Kruskalls, are both greedy. They're both impulsive sprinters. They just have very different running styles. So here's how they differ. Think of Prim's algorithm like a single growing organism. It starts at one city and greedily adds the single cheapest road that connects its little network to a city that's not yet connected. Kruskalls, on the other hand, is like a bargain hunter. It doesn't care about cities at first. It just looks at a list of all possible roads, sorted from cheapest to most expensive, and starts adding the cheapest ones to its network, as long as adding a road doesn't create a closed loop.
So, we have two different greedy methods solving the exact same problem. Which one's better? Well, it's time to go to the judge's scorecard.
Now, don't let the time complexity lingo scare you. It's just a fancy way of measuring how much an algorithm slows down as the problem gets bigger. For prims, its speed is tied to the number of cities, or vertices. That makes it great for dense graphs. Think of a map where almost every city is connected to every other city. Kruskal's speed is tied to the number of roads, or edges, so it really shines on sparse graphs, like connecting a few remote towns where there aren't many roads to choose from.
So let's zoom back out for the big picture. You've got the sprinter versus the planner. Greedy is all about being simple, fast, and making the best choice now. Divide and Conquer is about breaking things down to solve deep complexity, and it's built for teamwork in the modern world of multi-core processors. And that brings us to the most important takeaway of all. There's no single champion here. There is no one-size-fits-all best algorithm. It's all about understanding the specific problem you're facing so you can pick the right tool for that specific job.
So I'll leave you with this to think about. In your own life, from planning your week to tackling a big project at work, which approach do you lean towards? The quick, greedy choice or the strategic, divide and conquer plan? Once you start seeing the world this way, you start to see algorithms everywhere.